Welcome my dear students. Today we discuss the chi-square distribution, a most important distribution in the mathematics syllabus that will be contained in BSc, BStat and BTech. So the students who are belonging to these subjects, you must study this and follow this class. So here we discuss the chi-square distribution. To tell you about the chi-square distribution, we first tell you about the normal N01 variate, that is normal N01 distribution, that can be written in the form 1 by root over 2 pi e to the power minus x square by 2 dx, where minus infinity less than x less than infinity. So chi-square distribution defined as if x1, x2 and xn, if there are n independent standard normal variates with mean 0 and variance 1, then the sum of the squares of the n independent standard normal distribution is distributed as chi-square distribution. That is, chi-square equal to x1 square plus x2 square plus xn square, then chi-square is distributed as chi-square distribution with n degrees of freedom. To prove this, we use the method of induction. So let us first consider two distributions, x1 and x2, and we write the joint distribution function. That is 1 by root over 2 pi whole square into e to the power minus x1 square plus x2 square by 2 into dx1 into dx2, where x1 and x2 both varies from minus infinity to plus infinity. If we transform x1 and x2 using polar transformation, 2r2 theta 2 by x1 equal to r2 sin theta 2 and x2 equal to r2 cos theta 2, then r2 square equal to x1 square plus x2 square. As both x1 and x2 square and this term is positive, and so 0 less or equal to r2 less than infinity, and theta 2, here sin theta 2 varies from minus 1 to 1, so 0 less or equal to theta 2 less or equal to 2 pi. Therefore, the joint distribution function of r2 theta 2 can be written as 1 by root over of 2 pi whole square e to the power minus r2 square by 2 and the Jacobian and dr2 d theta 2 dr2 theta 2. And what is the Jacobian? That is Jacobian equal to del of x1 x2 and del of r2 theta 2, that is equal to del x1 del r2 of x1 and del r2 of x2, here del theta 2 of x1 and del theta 2 of x2, that is equal to, if we partially differentiate with respect to r2, then from it we get sin theta 2, and from this we get cos theta 2. So this will be sin theta 2 and cos theta 2. And if we partially differentiate x1 and x2 both by theta 2, then here it is r2 cos theta 2 and minus r2 sin theta 2. So that is this gives minus mod of r2 and this is r2. Therefore, the Jacobian is r2. So this Jacobian is replaced by r2. So this Jacobian is replaced by R2, and this is the joint distribution function of R2 and theta 2, where 0 less or equal to R2 less than infinity and 0 less or equal to theta 2 less or equal to 2 pi. Now as R2 and theta 2 we see here independent, and 0 to pi d of theta 2 equal to 2 pi, 0 to 2 pi d of theta 2 equal to 2 pi. So we write the marginal distribution function of R2 in this form: 1 by root 2 pi whole square e to the power minus R2 square by 2 R2 dr2 into 2 pi, and that can be written in the form 1 by root over 2 pi whole square e to the power minus R2 square by 2 R2 to the power 2 minus 1 2 into pi to the power 2 by 2 d of R2, and the limit is so. 0 less or equal to R2, 0 less or equal to R2 less than infinity, and R2 square equal to x1 square plus x2 square. Now we write the joint distribution function of R2 and x3, that is 1 by root over 2 pi whole cube into e to the power minus R2 square plus x3 square divided by 2, and R2 into 2 pi into d of R2 d of x3. This is the joint distribution function of R2 and x3: 1 by root over 2 pi whole cube e to the power minus R2 square plus x3 square divided by 2 R2 into 2 pi this 2 pi, and dr2 dx3, where 0 less or equal to R2 less than infinity and x3 varies from minus infinity to infinity. Again, using as we before this polar transformation x1 x2 to R2 theta 2, here we use the polar transformation R2 x3 to R3 theta 3, using in particular R2 equal to R3 sine of theta 3 and x3 equal to R3 cos of theta 3, and from these two R3 square equal to R2 square plus x3 square, that is equal to x1 square plus x2 square plus x3 square. So the joint distribution function of R3 theta 3 can be written as 1 by root over 2 pi whole cube e to the power minus R3 square by 2 here it is 2 pi and here it is R2 is R3 sine of theta 3 dr2 dr3 dx dr3 d of theta 3, and from this we have find the Jacobian R2, and here in the same way we can find the Jacobian J, that is equal to del of R2 x3 del of R3 theta 3, and this modulus equal to R3. So this Jacobian makes R3 is R3 square, as we before discussed. R2 and theta 2 are independent. Here it is also R3 and theta 3 are independent. So the marginal distribution function, as R3 and theta 3 are independent, and integration 0 to pi, and for this transformation the limits can be write as 0 less or equal to R3 less than infinity and 0 less or equal to theta 3 less than pi. You can see that here the theta 2 varies from 0 to 2 pi, but here theta 3 varies from 0 to pi. Why? Because here sin theta 3 equal to R2 by R3. Here both R2 and R3 are positive. Therefore, sin theta 3 is positive. And from the sine function, the positive value gives from 0 to pi. So, theta 3 varies from 0 to pi. So, the marginal distribution function of R3 can be written as. To write this, we first find 0 to pi sine of theta 3 d of theta 3, that is equal to beta of 1 comma half, that is equal to gamma 1 gamma half divided by gamma of 3 by 2, that is equal to root over 2 pi divided by gamma of 3 by 2. You know beta mn equal to integration 0 to pi sine to the power 2m minus 1 theta cos to the power 2n minus 1 theta d theta. So for this, here m equal to half and n equal to 1, because we write this 0 to pi sine to the power 2 into 1 minus 1 theta 3 and cos to the power 2 into half minus 1 theta 3 d of theta 3. So m equal to 1 and n equal to half. So the marginal distribution function of R3 can be written as 1 by root over 2 pi whole cube into here 2 pi, and we get from here root over pi divided by gamma of 3 by 2, from this e to the power minus R3 square by 2, and from this R3 to the 2 dr3 and 0 less or equal to R3 less than infinity. This can be written in the form 1 by root over 2 pi whole cube into 2 into pi to the power 3 by 2 divided by gamma of 3 by 2 into e to the power minus R3 square by 2 into R3 to the power 3 minus 1 d of R3 0 less or equal to R3 less than infinity. So we have already done the two cases for n equal to 2 and n equal to 3. For n equal to 3, we Already proved the marginal density function of R3 can be written as 1 by root over of 2 pi whole cube 2 into pi to the power 3 by 2 for n suman 3, this is 3, gamma of 3 by 2, that is for n equal to 3, e to the power minus R3 square by 2, that is n equal to 3, R3 to the power 3 minus 1, that is R equal to 3, dr3 0 less or equal to R3 less than infinity. Now we assume the result holds for n equal to m. Here m is greater than equal to 3 and it must be less than n So we write the distribution function of Rm that can be written as 1 by root over 2 pi whole to the power m 2 into pi to the power m by 2 divided by gamma of m by 2 into e to the power minus Rm square by 2 into Rm to the power m minus 1 into d of Rm, where 0 less or equal to Rm less than infinity. Now we want to show the result holds for n equal to m plus 1. We assume here this is true, 1 by root over of 2 pi whole to the power m, 2 into pi to the power m by 2 divided by gamma of m by 2 and e to the power minus Rm square by 2 into Rm to the power m minus 1 d of Rm 0 less than equal to Rm less than infinity. The result holds for n equal to m. We assume this and we want to show the result holds for n equal to m plus 1. If we can done it, then we reach the target. So the joint distribution function of Rm and xm plus 1 can be written as 1 by root over 2 pi whole to the power m plus 1 2 into pi to the power m by 2 divided by gamma of m by 2 into e to the power minus Rm square and xm plus 1 tar whole square divided by 2 into Rm to the power m minus 1 into d of Rm into d of xm plus 1, where 0 less or equal to Rm less than infinity and xm plus 1 varies from minus infinity to infinity. So this is the joint distribution function of Rm and xm plus 1. Now using the polar transformation Rm plus 1 xm plus 1 to Rm plus 1 theta m plus 1, which is in particular Rm equal to Rm plus 1 sine of theta m plus 1 and xm plus 1 equal to Rm plus 1 cos of theta m plus 1. So here r square m plus 1 equal to r square m plus x square m plus 1 and that is equal to x1 square plus x2 square plus dot plus xm square plus xm plus 1 whole square. Here what is Rm? Rm is x1 square, here Rm square equal to x1 square plus x2 square plus dot 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 plus xm square. Now here Jacobian, as similar Jacobian is also Rm plus 1, and the limit of Rm plus 1 is 0 less or equal to Rm plus 1 less than infinity, and limit of theta m plus 1, as we discussed above, 0 less or equal to theta m plus 1 less or equal to pi. So the distribution function of Rm plus 1, distribution function of Rm plus 1 theta m plus 1 can be written as distribution function of Rm plus 1 and theta m plus 1 can be written as from this 1 by root over 2 pi whole to the power m plus 1, 2 into pi to the power m by 2 divided by gamma of m by 2 e to the power minus Rm r square m plus 1 by 2 into, for this Rm we use Rm plus 1 sine of theta m plus 1. So Rm plus 1 whole to the power m minus 1 into sine to the power m minus 1 theta m plus 1, write this, and drm plus 1 into d of theta m plus 1, and the Jacobian is Rm plus 1. So Rm plus 1 whole to the power m minus 1 convert to Rm plus 1 whole to the power m, adding Jacobian. So this is the joint distribution function of Rm plus 1 and theta m plus 1. Here 0 less or equal to Rm plus 1 less than infinity, and 0 less or equal to theta m plus 1 less or equal to pi. Similarly, as we above previously discussed that Rm plus 1 and theta m plus 1 are independent. So as 0 to pi sine to the power m minus 1 theta m plus 1 d of theta m plus 1 can be written as 0 to pi sine to the power 2 into m by 2 minus 1 theta of m plus 1 cos to the power 2 into half minus 1 theta m plus 1 d of theta m plus 1. So we write this beta of m by 2 and half, and that converted to gamma of m by 2 gamma half divided by gamma of m plus 1 by 2, gamma of m plus 1 by 2. Now gamma of half equal to root pi. So root pi into gamma of m by 2 divided by gamma of m plus 1 by 2. So the marginal distribution function of Rm plus 1. Finally, we find the marginal distribution function of Rm plus 1 can be written as 1 divided by root over 2 pi, 1 divided by root over 2 pi whole to the power m plus 1, 2 into pi to the power m by 2 divided by gamma of m by 2 into, from this we have root over pi gamma of m by 2 into gamma of m plus 1 by 2 into e to the power minus Rm plus 1 square into Rm plus 1 whole to the power m into d of Rm plus 1, where 0 less or equal to Rm plus 1 less than infinity, and R square m plus 1 equal to x1 square plus x2 square plus dot 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 xm plus 1 square. So this is the marginal distribution function of Rm plus 1. If we simplify this, then we write 1 by root over 2 pi whole to the power m plus 1, and this gamma of m by 2 and gamma I am going to cancel these two terms, and 2 into pi to the power half and m by 2, these two makes m pi to the power m plus 1 by 2, and e to the power minus r square m plus 1 by 2 into Rm plus 1 whole to the power m plus 1 minus 1 d of Rm plus 1, and here divided by gamma of m plus 1 by 2, and 0 less or equal to Rm plus 1 less than infinity, where r square m plus 1 equal to x1 square x2 square plus dot 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 xm plus 1 square. So finally we have done the marginal distribution function of Rm plus 1, 1 by root over 2 pi whole to the power m plus 1. For Rm plus 1, this is m plus 1, 2 into pi to the power m plus 1 by 2. For m, this is m by 2, and here it is gamma of m plus 1 by 2 e to the power minus r square m plus 1 by 2 Rm plus 1 whole to the power m plus 1 minus 1 into d of Rm plus 1. So for m plus 1 normal distribution with mean 0 and variance 1, the sum of the squares of m plus 1 normal distribution with mean 0 and variance unity, we write here the marginal distribution function. We have already shown that the result holds for n equal to 2 and 3, and we assume previously the result holds for m, and now we have already done the result holds for m plus 1. So by the method of induction we write the result holds for any number n, any natural number n, and therefore the distribution function of n standard normal variates, that is if ChiSquare equal to x1 square plus x2 square plus dot 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 xn square. So if we write this m plus 1 for n, then the distribution function is 1 by root over 2 pi whole to the power n, 2 into pi to the power n by 2 divided by gamma of n by 2 e to the power minus Rn square divided by 2 into Rn to the power n minus 1 into d of Rn, where Rn square equal to x1 square plus x2 square plus dot 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 x1 square, and that will be chi square, and here 0 less than chi less than infinity. So the distribution function of chi square. So the distribution function of chi square can be written as finally we have reached the distribution function of chi square. Distribution function of chi can be written as 1 by root over 2 pi whole to the power n 2 into pi to the power n by 2 divided by gamma of n by 2 e to the power minus chi square by 2 into chi to the power n minus 1 d of chi, where 0 less or equal to chi less than infinity. If we simplify this, then 1 by 1 divided by 2 to the power n by 2 into pi to the power n by 2, 2 into pi to the power n by 2 divided by gamma of n by 2 into e to the power minus chi square by 2 into chi square to the power n minus 1 by 2 into d of chi. Then pi to the power n by 2 and pi to the power n by 2 cancel these two. We have 1 by 2 to the power n by 2 gamma of n by 2 e to the power minus chi square by 2 into chi square to the power. From these we remove 1 chi, then d of chi square, here d of chi square equal to 2 chi d chi, and these two supply here this, and from here n minus 1 by 2 we remove 1 chi, then we get x to the power chi square to the power half, then n minus 2 divided by 2, because here we write chi square to the power n minus 1 by 2, and if we remove 1 chi, then it reduces only minus half, and therefore chi square to the power n minus 2 by 2 and d of chi square, where 0 less or equal to chi square less than infinity. So this is the distribution function of chi square. So this is the distribution function of chi square, 1 by 2 to the power n by 2 gamma of n by 2 e to the power minus chi square by 2 chi square whole to the power n minus 2 by 2 d of chi square, and the distribution function of chi is 1 by root over 2 pi whole to the power n 2 to the power 2 into pi to the power n by 2 divided by gamma of n by 2 e to the power minus chi square by 2 into chi to the power n minus 1 d of chi. So this is the distribution function of chi, and this is the distribution function of chi square. And as there are n standard normal variates and the degrees of freedom, this chi square is n. So this is the distribution function of chi square with n degrees of freedom. Distribution function of chi square with n degrees of freedom, where 0 less or equal to chi square less than infinity. So the statement says if x1, x2, xn are n independent normal variates with mean 0 and variance 1, then chi square equal to x1 square, x2 square, dot xn square is distributed as chi square with n degrees of freedom. Finally, we have established here the distribution function of chi is 1 by root over 2 pi whole to the power n 2 into pi to the power n by 2 divided by gamma of n by 2 e to the power minus chi square by 2 chi to the power n minus 1 d of chi, where 0 less or equal to chi less than infinity. And the distribution function of chi square is 1 by 2 to the power n by 2 gamma of n by 2 e to the power minus chi square by 2 into chi square to the power n minus 2 divided by 2 d of chi square, where 0 less or equal to chi square less than infinity. So I have established this is the chi square distribution of n degrees of freedom, and this is the chi square distribution function of chi with n degrees of freedom. There are two different ways, distribution function of chi square and distribution function of chi, same thing. If we write chi square, then all the term in the form chi square, here it is also chi square, here it is also chi square, and if we tell chi, then the term can be this is chi and this is chi, and this is the chi square by 2 as usual. So student, you must follow this class and practice this. Here we summarize the total class. If x1, x2, xn are n independent standard normal variates, then the sum of the square of the standard normal variate is a chi square distribution with n degrees of freedom. We first established here for two normal distribution function, that is x1 and x2, and the sum of the square of the two normal distribution function is a chi square distribution of 2 degrees of freedom, and then we establish for 3, and then we assume this is true for n equal to m, where m is greater than equal to 3, and then finally we prove this for n equal to m plus 1, and by induction method the result holds for any n, and therefore the distribution function we have established here, the distribution function of chi is 1 by root over 2 pi whole to the power n 2 into pi to the power n by 2 divided by gamma of n by 2 into e to the power of chi square by 2 into chi to the power n minus 1 d of chi, where 0 less or equal to chi less than infinity. And the distribution function of chi square can be written as this way: 1 by 2 to the power n by 2 gamma of n by 2 e to the power chi square by 2 into chi-square whole to the power n minus 2 by 2 into d of chi-square, where 0 less or equal to chi-square less than infinity. You must study moment generating function, that is 1 minus 2t whole to the power minus n by 2, and then such properties. Thank you.